Today I'm going to attempt to baseline the battery charging infrastructure on my car. So this is the wiring diagram for it. The bit we're really concerned with is this area down here. But just to explain, you've got ground connections going off from the battery, and then you've got 12-volt feeds going through various fuses and junctions coming to the front of the car. Now, you're probably aware in both the BMW 116i and the LCI version. I know the LCI version is the same because I actually was working in this area on my neighbour's car yesterday. And she's got a 2007 BMW 116i. So whichever one of those you have, this will be equally appropriate. You have two circuits from the battery box in the back of the car going forward. One circuit goes into the fuse box, and then you have another thick wire that goes all the way to the front of the car and goes to the jump start terminal, which is in the engine bay. We can take a look at that in a second. Well, I haven't got it on my car, but I can show you where it is. And then the cable in a standard car, it goes across the engine bay through a bit of plastic conduit, and with a vacuum pipe is in the assembly, I think. And then it doesn't go to the starter motor as shown in this diagram. It actually drops down onto the alternator first, and then as a one-piece cable it then goes on to the starter motor. So the cable has like a connection lug for the alternator midway along the cable, and then the cable continues and drops onto the starter motor. So logically this diagram's correct. Physically it's not quite right, because we should have a connection from there to there and then one going back to the starter. So that's the 12-volt charging side, and obviously once the car's started, the alternator is charging the battery through this path back to the battery. The other thing we've got to consider on these alternators is they have a little data link thing called BSD, and you can see here we've got a data link connection going back to the DME. This, I believe, is bi-directional, so there are some commands that come this way and signals that go the other way, but I'm not completely sure. But what I will do is I will try and back probe the connection in the DME so we can see what it looks like under normal operation. So I'm going to start by measuring the voltage on the battery without the car running, and then we'll measure the voltage again on the battery with the car running. And let's see what we get from that. Okay, so here's the voltage without the car running, 12.6 volts. Now I'm using a racing battery. You maybe have a standard battery in the battery box at the back of the car. I can tell you, judging by my neighbour's battery, I was seeing exactly, well, not exactly, I was seeing 12.2 volts, I think. Let me just have a look. Yeah, 12.2 volts on her car. And that was a battery that was in good condition. Now at this stage, the battery is completely isolated, because in this car I have a battery isolator. So let's switch the power on in the car. Okay, so with the electronics running, you can see it's actually dropped a bit more, you know, closer to the voltage that I saw on my neighbour's car. Okay, let's try starting the car. Okay, as you can see, that's 14.3 volts. On my neighbour's car I saw 15 actually, but I would say that's pretty healthy. Okay, so I've stopped the car and I've isolated the battery again, so the voltage has gone up a bit. What I'll do now is we'll connect up an oscilloscope and we'll look at the ripple. So we should see some ripple on the feed from the alternator. So I will try and connect it closer to the alternator, although quite honestly I very much doubt we're going to see anything any different either from the battery or from the alternator. One thing I did on my neighbour's car when I was checking all of this was that I checked the voltage at the battery and then I checked it again at the jump start point in the front of the car. You probably want to do that with some stuff switched on. You want the circuit to be loaded. So if you do detect an excessive voltage drop, and by excessive I mean anything probably above about 150 millivolts, 200, let's say 200 millivolts, 0.2 of a volt. If you see a drop of that magnitude, not while it's cranking, because while it's cranking it will go, you'll get a bigger drop and the voltage will go down anyway. But just with light switched on and the ignition set to the second position, you shouldn't really see much more than 0.2, quarter of a volt or whatever. Before we do the oscilloscope measurement, it might be worth looking at what we should expect. So this is from some BMW documentation. Let me explain what we have here. We've got a single channel set up, channel 1, and it's looking at the ripple. So the ripple is because an alternator basically delivers, it starts out by producing a sine wave output. So something that goes up and down, up and down. Then that's rectified with, in this case, diodes in the back of the alternator, and then that's fed out into the battery. And what you're seeing is the result of the sine wave being rectified, and then there's probably some other things that slightly change the shape of the waveform, but this is known as ripple, and you get this on all sorts of power supplies. You can see that in this case the oscilloscope sets a 1 volt division per division, so each of these is 1 volt, each of these major divisions. It's each one of the, where have we got it, time base, so each division horizontally represents 1 millisecond, so 1,000th of a second. So the amplitude of this ripple, I can tell you from my experience, is about 300 millivolts, so about 0.3 of a volt. And I think if you eyeball that, that's probably about right, because it goes below the 0 point and above, and it's probably about 0.3 of a volt. So that's what we should be expecting. You notice they've got it set to AC coupling, so that takes out the sort of baseline 12 volt or 14 volt element and just shows you the ripple that's occurring. So here we've got the oscilloscope. It's connected up to the cable that comes out of my alternator. It actually, in my case, it comes into the passenger footwell in my car, but that's unique to my car. So you can do it from the jump start terminal. That's how I did it on my neighbour's car. Now what I've done is I've set the coupling to ground, which just gives me a reference point, so you can see ground is 0 volts, is right in the middle of the screen. Now let's change this to DC coupling just for a second. You can see that actually that's actually risen in the scale. So if I change the scale to 1 volt per division, here you can see that with my isolator on, so the battery supposedly is isolated from the car, I'm seeing about 1.2 volts. Now I don't know for certain, but I would imagine that this 1.2 volts is actually across some semiconductors inside the battery isolator, and that's why I'm seeing 1.2 at this point. But let's turn the power on the car and see what we get. Actually, we'll have to change this scale a bit, so let's change that to back to 5 volts per division. Okay. Okay, so at 5 volts per division, you can see we've got 5, 10, and you can see it's about 12 point whatever. So we've got our scope set up correctly, but at this point we've got it DC coupled. I will start it in this way and you will see the ripple, but we'll switch to AC coupling and look at the ripple in a bit more detail. Okay, so we'll get some noise on this circuit. It's not really showing the ripple in any great detail, is it? So let's change to AC coupling. And what we'll do is we'll increase the sensitivity of the scope. Okay, so that's now set to 0.2 volts per division. Let's stop it and see. I might have to change the speed a bit. There you go. And that is at 1 millisecond, just the same as in the documentation. I'm going to stop the car now. I have to stop the car quite quickly because it's on cold start. It's really stinks, and it I don't want to gas myself while I'm in here. I've got all the doors open, but yeah, it is a bit stinky. Okay, so you will get noise like this, these spiky bits, but you can see the ripple effect here. In the BMW documentation, they call this harmonic distortion, which I'm not sure it is a harmonic of the ripple, but whatever, it's noise. But what you can see is that this is working as it should, because if we look at the actual size of the ripple, in this case we've got 200 millivolts per division, vertical division, and it's not even making 200 millivolts. It's probably about 180, something like that. On my neighbour's car, I was seeing ripple values of around 300 millivolts. I think I actually saw a bit more than that as well. The main thing you're really looking for is something really unusual, like a massive dive in the trace at one point, which would show that one of the diodes has gone, or you're looking for things like that. If you've got something approaching what we see here, then that looks good. One further point I should cover, because it confused me with my neighbour's car, is the use of a peak-to-peak measurement. So you can see down here it says VPP, so my oscilloscope will measure the voltage from peak to peak. But of course the problem you've got is we've got these massive spikes in here which stretch right across the screen. So in this case, for this setting, that's 1.6 volts right there. So that's your first issue. And the other one is you notice the way you get this waviness sometimes in the waveform. I think it's because the DC component of the charge out of the alternator is varying, and if you take that point there to the top of one of these, you've got about 2.6 volts there. Sorry, not 2.6, 0.26 volts, as opposed to what we said was 0.18 volts. So you just need to be aware of that. So unfortunately, you can't really use a multimeter to do this. You do need to take a scope trace and then have a look at it, in a fairly stable condition. I think the situation with this car, when we did this trace just now, this car is completely cold. My car, because of remapping and the way it runs on open loop, you know, when it's not using the oxygen sensors properly, it's very stumbly and chuffy, and you know, it sounds like a traction engine when it's cold. And I don't think that helps with the fluctuation in RPM and hence probably fluctuations in the alternator output. It may be better if it was warmed up. The distance between each of these ripples is obviously going to vary with engine speed. So if you increase the engine speed, they're going to get tighter together, and you might have to increase the time base. But you know, this is, you only really want to know what the ripple looks like. You don't really want to do accurate measurements of it, I don't think. Okay, let's see if we can sort out this BSD connection now. Okie doke. I have the scope connected up, so I've back probed. Let's have a look at what I've done here. I've back probed the connection. It's a blue wire. It goes into the what's called the module 3, the third connector in the ECU. I think it's pin 19. Anyway, you can have a look on the wiring diagram. So that's going there, and I'm taking my ground from the main grounds that go into the DME. Yeah, so module 3 of the DME, pin 19 for the actual signal, for the BSD signal, and then I've got the ground connected. Don't worry about this, this is just noise. That's because the isolator is disabling the ground connection of the battery. So let's put the isolator on. That should stabilise that. What's that done for us? Okay, interesting. That looks like a signal already. Wow. So for the first problem is let's bring that, move that like that. I need to change it from AC coupled back to DC. And let's get some triggering in here. So for normal triggering, actually we can just stop it, can't we? Okay, not sure if that's what I expected. Bearing in mind that all I've done is applied power to the car, the ignition isn't on or anything. Now what I've done is I've pushed the key into the key holder. Again, no difference there. It's strange, obviously we saw this on the alternator main connection, this DC waviness. I'm not quite sure why you get that. Anyway, this looks very digital, doesn't it? With these little, looks like a really poorly formed square wave. Let's increase the speed. Yeah, there you go. Okay. I'm going to start the car now. Let's set the scope running. Okay, I would say that's now producing some form of data signal. I'm trying to think if there's any way we can stop it. So the thing you notice here is that we've got downward blips of different lengths, which looks to me like serial data. Yeah, this does, it looks like serial data. Let's increase this a bit. Yeah. I mean, obviously I don't know what it says, but you've got no form of decode. But I guess what we can take away from this is a normal waveform would look like a square wave, albeit it's got this sort of DC shakiness going on. The car's just switched to closed loop, I think, which makes it sound a bit better. Yeah, I would say that's what we're seeing. We're seeing some sort of digital, some sort of digital signal. Okay, I'm going to stop the car now. Okay, this possibly is going a bit too far geeky, but what I've done is I've placed a couple of cursors there, one there and one there, so that represents 1, 2, 3, 4, 5, 6 cycles, or 6 cycles of the signal, and that's in 4.94 milliseconds. And when I do the calculation, it comes out at that number there, 1214, but it's probably 1200 baud, what's called baud. It could be 1200 bits per second, or it could be a multiple thereof, depending on the way it's encoded. But I'll see if I can find some documentation. Not that it really matters. The main thing is that we've got the square wave. Once I got back to my desk, I found this really useful page. Of course, someone has managed to decode all this and knows a full explanation, as you'd expect on the internet. But there's this really useful diagram. Up here, what he's done is he's used a logic analyzer. So basically it's showing the same signal, but obviously in pure square wave form. And you can see that there's one type of signal which is called a sync bit, and then there's another one that's about double the size of these sync bits, which is this one, and he's decoded that as a 0. And then we've got one that's double the size of that, and that's decoded as a 1. So we've got sync bits, 0 bits and 1 bits. So this is just a form of pulse width modulation. Okay, we've covered a heck of a lot here, so let's try and summarize it. An isolated battery will produce 12.5 to 13 volts. With the car switched on, and for anybody who's not using battery isolators like race people, you just need to worry about that second number, which is 12.2 volts. With the car running, you see voltages of around 14 to 15 volts. 15 volts on an N43 LCI model is normal, as I've discovered, so that's quite normal. I looked back at my notes on my neighbour's car and I saw a ripple of up to 350 millivolts on that. Then we come to the serial link, the BSD link. So it's a blue wire on its own separate plug that goes into the back of the alternator. It goes from the alternator to the DME through the module 3 plug on pin 19. It's carrying a pulse width modulated square wave. I didn't cover this actually, you may not have noticed with the scope, but it's actually a square wave that swings between 0 and 12 volts. The frequency of the signal on there is 1200 Hertz, and it's actually representing a data rate of 1200 bits per second. We didn't look at the full decode, but what we do know is that a sync bit, which is used to synchronize the clocks each end of the link, that's the narrowest of the downward pulses. Then you've got the 0 bit, which is twice the length, and then you've got the 1 bit, which is twice the length again. Okay, so I hope that helps you. Although, you know, we went into all the stuff about the pulse width modulation, it doesn't really matter. If you've seen a square wave on there, albeit a bit shaky, that should be good. And then we've got the ripple and the base voltages on the main connector into the alternator. Okay, catch you on the next one.